Hello everyone and welcome to the hydrolysis of a polyester lab. For this lab we're going to take a sample of PET or polyethylene terephthalate, oftentimes stamped with a recycle code 1 on the different things that we could use, and we're going to cut that up and weigh out about 0.5 grams of it. So let's watch that. We're going to zero the scale, and then a plastic container which was labeled with recycle code 1, which is PET, was already cut up. And that is now being added to the weigh boat. Looking at recycle code 1, hopefully you can see what that, so this is recycle code 1 right here, and this is a repeat unit of polyethylene terephthalate. So on the scale we have 0.51 grams of polyethylene terephthalate. That's one of the starting materials we're using in this reaction. Another crucial starting material that we need is potassium hydroxide, or KOH. Specifically, we need 2 equivalents of that. Hopefully you have your table started. I think that we need about 1 gram of potassium hydroxide. Looks like 1.04 grams, a little bit excess potassium hydroxide isn't a problem. So we've got about 0.5 gram of our PET, just over 1 gram of our potassium hydroxide, and now we need about 30 milliliters of our solvent, 1-pentanol. So our solvent, 1-pentanol, right here, is right here. We've got 1, 2, 3, 4, 5 carbons in our chain, and an alcohol functional group connected to carbon 1. So that is 1-pentanol. We've got 30 milliliters of 1-pentanol, and now we're going to add our potassium hydroxide into the round bottom flask. Ideally, we'd use a metal spatula to scrape that in. Also, if you have potassium hydroxide exposed to air for too long, you're essentially going to form water pretty quickly, so you really want to weigh that out, put that right in the round bottom flask. And now we've added our 30 milliliters of 1-pentanol, or our solvent, to allow all of our compounds to interact. And most importantly, we need to add our plastic, our PET. In lab, I'd probably recommend cutting these into smaller pieces, exposing more surface area for the reaction to happen. We'll see how this goes in this experiment. Okay, now we have our reflux condenser connected, and we have water going in the bottom of the condenser and out the top to cool that condenser down, making sure that as it starts heating, which you can see, we don't end up boiling away all of our solvent, 1-pentanol. You can see as the round bottom flask is heating, we are starting to reflux. So we've got our solvent that is evaporating on the round bottom flask and then condensing back down into the bottom of the round bottom flask. So there's our condensation liquid there and there at the bottom of the condenser, and you can see that fall right back down into the bottom of that round bottom flask. Okay, at this point in the experiment, we have added our water, and now our round bottom flask is separated into two layers. So we have water on one layer and one pentanol in another layer. Water is more dense than the organic solvent, one pentanol, so that's going to be the bottom layer. We're going to mix that up well. We had a lot of potassium hydroxide in our reaction, so when we look at our intermediate that formed from the reaction, we have our carboxylate anions that form, so a negative charge on the oxygen and then a positive charge on the potassium. So we have a salt which is going to be soluble in water. So our aqueous layer again is at the bottom of our round bottom flask. That is going to then be at the bottom of the separatory funnel, and that aqueous layer is going to contain our intermediate, our potassium carboxylate intermediate. We're slowly decanting because if you look close, you might be able to see quite a bit of that plastic left. So that plastic was pretty thick. Some things we could have done are reflux it for quite a bit longer. We also could have heated it maybe a little bit warmer, had it stirring a little bit more rapidly in solution. All those might have brought the reaction a little bit further. But we have quite a bit of starting material left over in that round bottom flask, which will be evident as soon as we decant all the liquid out. And again, that potassium carboxylate salt, that potassium carboxylate intermediate, is in the aqueous layer. So the bottom layer, or the clear layer in our separatory funnel, is where our potassium carboxylate intermediate is. And that is a salt. We've got ionic bonds in it, so that's going to be soluble in water or fully suspended in that aqueous solution. And there's quite a bit of the plastic left over. All right, in the separatory funnel, after intermixing those layers pretty well, now we're going to separate the two layers. So we're going to separate the bottom layer, or the aqueous layer, from the organic solvent, which is the 1-pentanol. And again, in that aqueous layer, we have our potassium carboxylate intermediate. We're going to add a little bit more water, and we are going to intermix those solutions pretty well again to extract any of the potassium carboxylate that remained in the 1-pentanol from that organic solvent. So once we extract any remaining potassium carboxylate from our organic layer, we are then going to separate the layers again. So once those layers have separated, we can now again remove that bottom layer. What we're doing here, conveniently, since water is more dense than organic solvent, now we can combine our two layers into that beaker. So we're essentially combining two layers of aqueous extraction into that beaker. All right, we've removed all of that second aqueous layer. And we're going to test that solution to see how acidic or basic it is. It looks like it's purplish blue, so we're pretty basic. We're around a pH of 12. You can't get much more basic than that, which makes sense because we had excess potassium hydroxide in our solution. We have our potassium carboxylate anionic salt intermediate in that solution. Now, that is water soluble. You can see when we keep adding our 10% hydrochloric acid, now we've got precipitate coming out of solution. So that white solid that you saw form is now precipitate coming out of solution because no longer are we going to have those ionic bonds between our potassium and our oxygen. Now we're going to protonate our carboxylate anion into a carboxylic acid. Once we deprotonate that and we no longer have ionic bonds in our salt intermediate, in our potassium carboxylate, we're going to have two carboxylic acids, and this compound here will not be as soluble in the aqueous solution as this. So that's why you see the white precipitate coming out of solution, or the what is no longer a salt crashing out of the aqueous solution. Now that we test the solution, we see that we've added plenty of hydrochloric acid. We have a very acidic solution around a pH of about 2. And my guess is that now all of our potassium carboxylate is protonated. When you look at the pKs of a carboxylic acid, you're around 4.76. Once our pK is less than that, then all of our carboxylic acids, or all of our potassium carboxylates, will be protonated into carboxylic acids. Now that we have that precipitate in our aqueous solution, we're going to do vacuum filtration and collect that precipitate on filter paper. All right, right now we're lifting up that filter paper. Let's stop there on the video. So essentially we're going to put the filter paper on our watch glass, and then we're going to put that over our beaker to let it dry out. It'll take a long period of time. I'm just going to give you the data for the end. So let's actually look at the worksheet a little bit more. So like I said, we added our 3 starting materials: our plastic, our polyethylene terephthalate, we added our strong base and strong nucleophile potassium hydroxide, and we added our 1-pentanol solvent. In the reflux condenser, once this refluxed for 30 minutes, we converted quite a bit of our plastic into our intermediate, our potassium terephthalate intermediate. Once we stopped refluxing, organic solvent, which had our potassium terephthalate in it, and we added water to extract our potassium terephthalate from our 1-pentanol organic solvent. We then allowed our dicarboxylic acid product to crash out of the aqueous solution by adding hydrochloric acid. For the table of reagents, hopefully you are able to take the 1.04 grams that we isolated, figure out the molecular weight of potassium hydroxide. You can look that up on Wikipedia or Sigma Aldrich, figure out the molecular weight, and convert that to millimoles. For our polyethylene terephthalate, I think we started out with 0.51 grams, 0.51 grams. And for our hydrochloric acid, that wasn't clear how much we added there. So let's go with 15 milliliters in total for our 10% hydrochloric acid. Hopefully when you calculate this, you'll see that PET is our limiting reagent. So PET is the limiting reagent. Once you figure out that number of millimoles that we used for our starting material, that is the theoretical yield of terephthalic acid. Based on what we saw in the experiment, there's no way that we are going to experimentally reach the theoretical yield of terephthalic acid, considering we still saw quite a bit of PET starting material after we stopped refluxing. Now let's look at the mechanism down here. There's a pretty good layout of the mechanism. This isn't the correct version of the mechanism, so let's talk about what's incorrect and what is the actual correct version of this. So here we have our PET, our repeat unit of our polyethylene terephthalate. Here in the mechanism, we have our hydroxide anion attacking the carbonyl carbon of our ester functional group. I agree with this arrow. The electrons from the oxygen are attacking that carbonyl carbon, but once that attacks, these electrons here in this from the carbon to the oxygen are actually going to go up to that oxygen. The electrons need to keep flowing in that same direction of the original nucleophilic attack, so these electrons need to flow up here. That arrow is incorrect. When you do this attack and your hydroxide anion attacks the carbonyl carbon, push these electrons up to the oxygen, this is what intermediate you get. So this is the OH. So this is the hydroxide anion that did the attack. That's no longer a double bond because those electrons moved up to the oxygen, putting the negative charge on the oxygen. In the next step, now we're going to break our polymer chain. So here, once we have the negative charge on the oxygen, I agree with the first arrow. The electrons are going to come down, reform a double bond between the oxygen and the carbonyl, what was the carbonyl carbon. And then these electrons are going from this carbon-oxygen bond are going to go sit on the oxygen. This arrow is incorrect. That never happened. That bond never broke and will never break, as you can see here and here. So once we do that, we've essentially broken our polymer and we formed one of our carboxylic acids. Now it's important to note in this mechanism, we're not specifying formation of both carboxylic acids. We're just showing essentially one carbonyl carbon being attacked. But in order to get to here, it had to happen to both sides. So we definitely missed out on our other equivalent of potassium hydroxide attacking this side. It's just a little bit redundant to do it twice for the mechanism. So I just want to clarify, even though we're literally only showing one equivalent of potassium hydroxide being used in this mechanism, it's actually happening twice, and this is where it was missed. So if we want to bring this in and attack that carbonyl carbon right there, we could show that. But we also need to show another thing that's happening, and that is once our leaving group leaves, we formed a carboxylic acid, but we also formed a very strong base. So we formed an alkoxide anion here, which is an oxygen with a negative charge on it, not connected to a carbonyl carbon. So that is our alkoxide anion that we formed. That's a strong base in solution. If this is mixed in with this in a solution, this alkoxide anion will definitely deprotonate our carboxylic acid. So to show that in the mechanism, we're going to use our alkoxide anion as our base. That's going to attack an acidic proton, which it did here. That's fine. And then these electrons from the oxygen-hydrogen bond are going to go to the oxygen to form our carboxylate anion, which as represented above as our intermediate, it was represented as this because we know we have potassium floating in solution. So whether you showed it like this or like this, either of those are okay. Specifically, it's okay if you show it with a negative charge on it. It has a negative charge on it. It's okay if you show the other cation next to it and overall being neutral because that means the charges have canceled each other out when the other cation is next to it. So both of these are okay representations. All right, once we have our carboxylate anion, we actually have two carboxylate anions. So our intermediate that we looked at above, I'm just going to redraw that here. So we've got our aromatic ring, and we've got our oxygen with a negative charge there, and we have our other carboxylate anion there. At this point, that is when we add the hydrochloric acid. So really, in some ways, this skipped two different steps where we said, okay, this other carbonyl carbon was automatically converted to a carboxylic acid, and then it was converted to the carboxylate anion, and then converted back to the carboxylic acid. So a lot of things were missed in this. But again, we're just practicing arrow pushing mechanisms here. So we did form a carboxylate anion as shown here. That needs to be protonated by the hydrochloric acid. So the electrons, our electron source is the carboxylate anion, specifically the oxygen with a negative charge of our carboxylate anion. That is going to attack the proton on the hydrochloric acid. So I agree with this first arrow. These electrons are going to go attack and form a bond with this hydrogen. I disagree with the second arrow. When the electrons go to the chloride anion, or the chlorine to make the chloride anion, they are not coming from the hydrogen. That hydrogen doesn't have any extra electrons on it. They're coming from this bond here. So that bond is going to break. Those electrons are going to go to the chlorine. And so the byproduct of this reaction is plus Cl-, And in order for these electrons to attack, that means our potassium has to be free floating too. So we actually have potassium chloride as our byproduct. All right, that is the mechanism example that I want you to show. You only need to show essentially conversion of one of the esters into the carboxylic acid. You can overlook the other, or you can show the other, whatever you want to do. It'd be good practice if you just showed both, but whatever you want to do is fine. All right, so we saw this part of the procedure already. Essentially, once the solid was no longer soaking wet, that's what we saw. It was still soaking wet. We didn't spend too much time waiting to finish the recording. So let's say that we isolated 0.20 grams of product. So if you're not able to come to lab because we're all not there or you can't be there, this is the value that I want you to use. 0.20 grams of terephthalic acid was isolated. So that essentially is what we would look at on day 2. Looking back at the table of reagents, we looked at some specific data there. One important piece though is the melting point of terephthalic acid. So make sure you look up that melting point, think about why we didn't actually take that melting point in lab, and also fill in the rest of the table. So essentially fill in the molecular weight and amount for 1 pentanol, water, and the rest of the compounds. We've already talked about the importance of the limiting reagent to figure out the theoretical yield. Within this lab report, hopefully you've thought quite a bit about different ways, based on what I've talked about, for how we can actually increase the yield of this reaction. So this is going to be a relatively low yield. We could literally see starting material still left over, which in this case it's advantageous that we were starting with that plastic, because rarely for organic chemistry reaction can you actually visually see the starting material left over in your flask. So we had solid evidence right there that the reaction did not go to completion. All right, one last thing I want to talk about is the fact that we did a hydrolysis reaction. We added water. That does not mean that the hydrolysis reaction happened when we added water into our round bottom flask to separate the 2 layers. So remember, and let me just draw a round bottom flask here. Remember, in the experiment, we had a round bottom flask. We had 30 milliliters of 1 pentanol, 1, 2, 3, 4, 5 carbons, and an alcohol functional group. So we had 30 milliliters of 1 pentanol there, and then we added water in here. So once we added water in here, this separated then into 2 layers. We had more volume of solution, and that was our water layer. This is not what a hydrolysis reaction is about. So we did indeed do that, that's true, but the hydrolysis reaction is about literally adding the equivalent of water to our molecule. So when we specifically added water to our molecule and broke bonds apart to form 2 separate compounds, in this case hundreds of individual compounds from the polymer, the hydrolysis reaction was adding the hydroxide anion in this step, where we essentially had our hydroxide anion attack our carbonyl carbon of our ester. And then in the last step, when we protonated our carboxylate anion, that was the other hydrogen. So in total, what we added was hydroxide anion and a proton. Overall, in total, that means that we added water to our original polymer. So that is what it means to do a hydrolysis reaction. Adding the sum of molecules that we added is water. All right, that is all for the video. Hopefully from the video you are able to answer these questions, think about different ways that the experiment can be improved, and if nobody else did this experiment, don't worry about getting another group's data. If other groups did and you just weren't able to be there, then definitely get other groups' data, talk to them about what they saw in the reaction, and how that compared to this video or compared with other groups.